I hope I'm audible. We can wait for 2 more minutes, let a few more people join and then. Okay, let's start. So welcome everyone. We are discussing about what was covered in week 5. We will briefly go over what were the concepts that were covered. Basically, this week was all about fibers and propagation of electric fields through a fiber. Next week, we'll also continue our discussion on fibers, but it will be focused on dispersion. The content is live already. Although I would imagine this week's content was difficult to actually go through the videos, but the assignment itself is not very difficult. I don't think any of you should have any problems. If you have, you can ask either chat or ask directly. So this is a brief recap. So we started our discussion with the structure of optical fibers. Then we started with the ray picture, which should have been familiar with all of you. So these discussions on total internal reflection, Snell's law, then acceptance angle, critical angle, numerical aperture. This numerical aperture will be used in the wave picture also. That ray picture was described to you. Then we talked about the attenuation mechanism in fiber, and we briefly mentioned this Rayleigh scattering also. Just on another note, this Rayleigh scattering can be used for some sensing applications also about the fiber. This is not the focus of our course, but for monitoring the health of a optical fiber, you can use such loss mechanisms also. Then we briefly introduce the concept of modes using the ray picture. So although ultimately we will be solving the Maxwell's equations and how that is where we will define the guided modes and those concepts. But the ray picture is enough to show you that not all angles of incidence are supported. So here we use this ray picture with the concept of wavefronts. Only those rays will be supported in the waveguide where the wavefronts are interfering constructively. So example questions from this ray picture could be, you could be asked to find how many modes are supported in a fiber. You can get to an answer from this ray picture also. You will probably need calculators and all, but theoretically this can also be done. Then we went on to the main portion of this week's discussion, which was about finding out these fiber mode profiles, how the electric field distribution looks like, which is not a plane wave because we are talking about a dielectric structure. And we also discussed about what are the assumptions we are making. So we'll be discussing about linearly polarized modes. Basically, we are solving the scalar Maxwell's equations, assuming that the both polarizations are supported. So you can also solve using vector equations. You might find the treatment in other textbooks like Yadiv and other. If you're interested, we can refer some textbooks, but more depth is not required for a technology course. So this much depth is sufficient. Then while solving for the modes, we ended on this universal BV curves. There were multiple the curves and how this like normalized propagation constant and this phi number, how using these information you can say how many modes are supported in a waveguide for a given wavelength. And then we talked about how although the radial profiles are actually Bessel functions, we can approximate them using Gaussian function, especially the LP01 mode, which is the mode supported in single mode fiber. And there we briefly mentioned the concept of mode field diameter. So where at what distance does the power the electric field amplitude fall to 1 by e squared of the maximum value. And we talked about Marquis's relation. So I think that relation is asked to, like, you're asked to use that relation, overlap integral and coupling efficiency. This is an important concept, but while using single mode fibers, and like if you use all of the fiber coupled components, we'll try to show you some of the components later. There you are not manually handling this matching the mode profile so that maximum power can be coupled, but it will become a concern if there were examples given in class also where the mode profiles are not matching, you're coupling different kinds of fibers and so on. So this is an important concept, but we're not going into much depth in discourse. Basically, you can calculate how much power is getting coupled into which mode by using these overlap integrals. And for any incoming mode, you can deconstruct it into the supported guided modes, and then it's basically like Fourier transform, but instead of breaking a wave down into sinusoids, you'll be breaking them into different mode contributions. So from this content, I think these are the equations that will be these are the equations that will be used for this week's assignment and all. What are omitted are how we solve the Maxwell's equations. Those equations are these ones. So basically, we started with our ray picture. This is the critical angle. Then this is the numerical aperture. This this N naught is the so this N naught is usually assumed to be like air. So N naught will be 1. So numerical aperture will be only usually the expression you will see is only this upper part. Then we just told that Rayleigh scattering is proportional to 1 by lambda raised to the power 4. Then we also talked about macro bending loss, how it is how it depends on how tightly you wound the fiber. So if you make a sharp bend in a fiber, there will be losses. I mean, if you make a too sharp a bend, the fiber will break. But even before that, there will be noticeable losses. Then this equation came from the ray picture, how we first introduced the concept of modes, how there could be discrete number of these theta angles for which the rays are supported. Then here is a big skip of 5 videos. And after solving those Maxwell's equations, we ultimately ended this how the mode profiles look. We define them using this LP, LM, and based on this L and M, you can tell how the mode will look like. So you will have this M-1 zeros in radial direction and 2L zeros in azimuthal direction. From there, you can map from either, you can tell that how LP, LM mode looks like, or if you see a electric field or an intensity profile of a mode, you can tell that this is which mode. Then V number, which you first see as this parameter that is independent of beta while solving this Maxwell's equations. So this is again you must have seen it if you have done any course on an introductory course on photonics. So for P number below some specific value 2.40 2.408 you will not your waveguide will not support any modes higher than LP01. So those waveguides will be termed as single mode. So this V number is the important parameter. Then for large V numbers, you can approximately say how many modes are supported. Then from mode field diameter, we get this Marcuse's relation, which is an empirical relation valid only for this range. So from here, you can tell about the mode field diameter. And finally, we end on this coupling. This is the overlap integral, which will give you information about coupling efficiency. And basically, while solving for the modes, we assumed this form. This should be inside brackets. So we say that the mode information is contained in this part. Then we basically we have not used the term n effective in our discussions. I think briefly it was touched on that the refractiveness profile will be like n1 here, n2 here, and the beta values for the modes that you find, they will be somewhere in the middle of this n1 and n2. That is the additional constraint that we put. Like for guided modes, this will be true. So you can also have radiation modes where there are no such constraints. Then while solving, we separate the variables and find this the azimuthal dependence here and the radial dependence here. Then to simplify, we introduce this U and W. And V was first introduced as a way to get rid of this beta square, which was yet unknown while solving this Maxwell's equations. So that is where we first encountered V as this, which this equation you've already seen. And we also define the normalized propagation constant B as this, and B values will be constant within 0 and 1. So yeah, that's pretty much all of the equations and all of the theory that was covered this week. If you want to look at the specifications of this single mode fibers that are commonly in use, you can look at ITU recommendations. Which is single mode fibers are specified in G652. You can just search and okay, mode field diameter, I'll briefly touch. So yeah, if you're curious, you can look at the specifications for single mode fibers. Here, ITU-T is concerned with optical fibers, those specifications. Other branches may give recommendations about wireless networks and all. And G652 is for characteristics of single mode optical fibers. If you want, you can look at the PDF if you're curious. Okay. So for a fiber with so a fiber like this, like your LP01 mode will look something like this. This is electric field intensity, and this is a position. So how we define mode field diameter is like you plot, this will be the core. So this electric field intensity will be maximum at the core, and it will it will follow Bessel function, but you can approximate using you can approximate by using Gaussian distribution. Like Bessel function takes that complicated form, you know, and Gaussian will be e to the power minus x squared by 2 sigma squared something. So mode field diameter is defined as the I'll have to look at whether it is electric field, whether it is mode of electric field or mode of electric field square. I'll have to. I just got confused, so it's probably not this. It's probably not this, but confirmed from a book. Okay, but mode field diameter basically says that your mode will here it will look like a spot, no? Like it's more intense at the center, and it falls off. So mode field diameter defines that this is the maximum value. Say A is the peak. So what will be A by E square? What is the distance from the center where the value falls off to 1 by E square of the maximum value? That is the so this much will be like mode field radius. Mode field diameter will be this distance. For that, you like to find this mode field diameter. You don't have to plot these functions and all. You use Marcuse's relation, which is this one. So especially going by what is asked in the assignment, they're always asking you to find the V number first. Once you have the V number, you can substitute that here. So you will get this W by A. And what you're asked about is what is W? I think the terminology was W naught or something for the first mode. So the concept is that like the maximum power for LP01 mode will be at the center, and they're asking at what diameter. You can consider that all of the power is within that diameter. So below 1 by E square, we ignore the this power in the tail. That is the concept of mode field diameter. A is this so if A is core radius, I'm again confused about radius and diameter. Okay, so find it from the reference book, or I'll check and post in group.
Sir, A is the core radius.
Yes, A is the core radius. A is given
Yes.
for.
A is the core radius and W is the spot size. And 2 multiplied by W will be the mode field diameter.
Yes, okay. W is not the diameter, then W is the radius.
W is the spot size.
Spot size means this only, like Where
Okay.
does it fall to? 1 by E square.
Yes.
So this will be W10. The mode field diameter will be 2W. So basically, this is the concept of the mode field diameter. I'm confusing with this radius and diameter because A is radius, I know, but W and 2W I got confused. So this is also. And video lectures 51. Ma'am gave example of V and mode field diameter. She did not complete the mode field diameter answer. Oh, okay. I'll give an example question, solved question. I'll post. I keep saying that I'll post in the morning, but like I'll probably post before afternoon. Like, the textbook followed is I think Ghatak and Tyagarajan, ma'am has mentioned, but I'll see if other textbooks will also cover these concepts. We're not going too much in depth. If you want depth, and like if you want to numerically solve and all, you can. Because the book is named Introduction to Photonics by Yardif. This is too much in depth. We don't need this much depth. And if you want to actually solve numerically, we will try. I will try to have one example shown in MATLAB or something that you can look at. There is one old book which is not specifically look at. It doesn't specifically focus on fibers. But it's a very old and good book on EM waves. I think both the writers have passed away, but uh, the solution to the Maxwell's equation in vector form, if you want, you can look at some advanced textbooks. It is absolutely not required for this course. Just for curiosity, if you have time, you can look. Approximate number of guided modes is this. Also, you can look at, you can just search, Google will have answers. One reputable source is also this, it is like web pages with short descriptions of concepts. Some of the concepts will not be covered also, but so this website is reputable. We also use it. It looks something like. So the website looks something like this. You can use it. So when in doubt, you can go to textbook, or if you're too lazy, you can use this website. Otherwise, I don't think this mode field diameter is something you guys are a little confused at, I guess. But otherwise, the assignment this time should not be very difficult. It's all asking about this LP, LM modes, how they look like, what relation does beta have. Then you're given some tables, and instead of giving n1, n2 directly, they're giving you n1 minus n2 by n1 delta value. By the way, that you can use. Okay. So numerical aperture is given as this value, no? Sometimes you will also have it in terms of delta. This will be given some small value. So assuming that this is small value, you can sorry. What you can do is a square minus b squared. You can expand. This we will approximate as 2n1. Then we'll use n1 minus n2. And we want an n1 in the denominator, we can use. So using this much tricks, you can have this relation also. So instead of using this like seeing this expression, you might be using this expression. Both are equivalent if this delta is small enough. So like V number is so here this part you can either use n1 square minus n2 square, or you can also use n1 2. I mean, you will arrive at the almost same answers. These are equivalent provided this provided this is going to 0. That's all. I think the assignment question is giving this delta value again and again, and 2 you have to find out. Mode field diameter I'll try to clear up. Otherwise, like although the course content was difficult this week, I don't think the assignment itself is difficult. You should not have any trouble. If you have trouble, use the discussion forum. That's all. Also, I think there is some misconfiguration. So the solution to the assignment, it is configured as last year's assignment, which was some MATLAB based something. It's not. So it will take a couple more days to have the solutions published. So solutions will be published, but they will be for previous year, not the questions from this year. So we'll have it fixed in 2-3 days, I think, or release it later. But those answers are also, you can have a look at it. The solutions won't be public right after the assignment deadline. You will have to wait 2-3 days. That's all. LP00 is not possible like that. There is no meaning. LP00 will probably look like what? The plane wave. Like it's not a guided mode. Like the counting starts from LP0. That's all. I mean, there is no deeper meaning. Just we start counting at LP0. Like if you put m equal to 0, I think the solution comes as r equal to 0 everywhere or something. So it has no meaning. Okay, if there are no more questions, we will stop. By the way, last year's assignments asked you to use MATLAB to solve these transcendental equations that you saw in towards what solving part video 5 or something. You encountered those Bessel function something like this, no? You encountered. So those transcendental equations you can solve graphically. What was shown in class also, those graphs were shown. Last year's assignment was also like this week's assignment was easy only, but you were asked to change some values in MATLAB script and run the MATLAB script. So like if we make that solution also public, like you can have a look at. I mean that was the question. You can have a look at it, how we go about solving. That's all. Okay. We can stop, I guess.
Thank you, sir.
Okay. And so far we have found mistakes in the assignments, no? Those questions will be like, their weightage will be made into 0. Wrong questions.
Okay, sir.